All right, hello everyone. Back for section 3.4. So we're going to move back into derivatives. We kind of get away from it for like one day. Not really. We still do some derivatives. We're going to look at some applications, and then we'll learn how to take some more derivatives in the next couple sections. So right now is probably the most important application of derivative. Um, and this is why they gave it a special name too. So we're going to go back to velocity and rates of change. So I'm sure you already know this. You've seen it in physics class, probably, but you saw it last year or so. We'll go a little bit quicker through it. But it's basically the idea that when you're dealing with distance traveled and speed and acceleration, that they're all connected by math and they're all connected by um, derivatives. So this section is titled Velocity and Rates of Change. So just a little notation first. Notation not so important. It's just the idea that's most important. We're going to do some Algebra 2 review today also. So displacement would be how far something's moved. So typically we use the letter S for position. Okay, that's a common terminology in math is S is position. So delta S would be change in position. Change in position is just how far you are from where you started, right? So it's the position at time t plus some change in t, so like a new time. So delta t is the change in time. So that would be like our second position minus our first position, S of t, right? Nothing earth shattering there, just a notation for displacement. Average velocity then, which we did back at the beginning, first thing I did, I think, in this class, would just be how far you've moved over time, or displacement over time, which is the delta S over delta t. And notice what you get is something that looks like a derivative, right? Or a tangent line. And it is. If you were to try to find instantaneous velocity then, right? The instantaneous velocity would be the limit as that delta t approaches zero, okay? And then that just becomes instantaneous velocity. So we give it a name, which is velocity. So the velocity is equal to the derivative ds, remember, derivative of s, derivative of position over dt. So this is just s prime. So velocity is s prime. It's just the limit as delta t approaches zero of f of t plus delta t minus f of t over delta t. It's just derivative. So all you really need to know is that the instantaneous velocity is the derivative of the position. So if you had a position function, which we're going to give you in just a second, the derivative of that would be the velocity function. And we'll go one step further, and I'll jump back here. The acceleration would be the derivative of the velocity. Okay, so acceleration is acceleration, derivative of the velocity, or the second derivative of the position. So positions, we start with S. We start with VT. Sorry, S of T is position. Velocity is the derivative of the position. Okay. And then acceleration is the derivative of the velocity, which is the second derivative of the position. Okay. Speed. Sometimes you hear the term speed. Speed and velocity are just a little bit different, right? You probably know this from physics and other math. That speed, velocity has a direction. So velocity can be left, right, up, down, positive, negative. Whereas speed does not have direction. It just has, it's just a positive number, right? So speed is just the absolute value of the velocity. All righty. So the most common use of this is in projectile motion. So this is going to be an Algebra 2 review. The problem I'm about to give you is actually straight out of an Algebra 2 book. But you can use some calculus to solve it that maybe you didn't use back at the beginning. So it's projectile motion. So we have a formula for projectile motion. You need to have these formulas memorized for sure. You need to know them. We'll talk about where they come from later on in the course for sure also, but right now we're not quite ready mathematically. So projectile motion, if you're in feet, okay, feet in inches is negative 16t squared plus the initial velocity times time plus the initial height. Okay, if you're dealing in the metric system, it's negative 4.9t squared plus the initial velocity times time plus the initial height. The negative 16, the negative 4.9, you probably recognize maybe as half of the gravitational constant. Whether you're in feet, it's 32 feet per second squared, and in meters, it's 9.8. So that's where those formulas come from. Yes, you do need to know those formulas because you're going to get a question that looks like this with some information, and you're going to be asked some questions about it. So you need to build that formula, right? So in this particular example, we got a rock that's launched upwards, straight up, with a velocity of 160 feet per second. And then I'm going to ask 4 questions here, which are pretty much the same 4 questions, except for maybe the velocity question or acceleration. But it's the whole idea is like you answer these questions in Algebra 2, where they would ask you things about this motion. So the first thing we're going to do is we're going to write an equation for the position. So we're going to use that projectile motion equation, which that's why we need that equation. It's negative 16t squared, okay, plus the initial velocity. So that initial velocity is 160 feet per second. So plus the initial velocity times time, plus the initial height. This was launched, it doesn't really say, sorry, I guess I should have said this. It launched from the ground. So our initial height is 0. Okay, so I'm just going to leave that off, but there would be a plus 0. So you remember this motion back in Algebra 2 is just a parabola, right? So in Algebra 2, you found all those things about the parabola, right? They might ask you, find the vertex of the parabola, find where the parabola intersects the x-axis, that sort of thing. So same basic questions. How high does it go is the first question here, right? How high does it go? Think about it, goes up, starts somewhere, goes up, and comes down, right? So how high does it go is just the vertex of that parabola. So if you wanted to for this problem, you could use Algebra 2 or Algebra 1 actually and find the vertex if you remember how. I'm not going to remind you that because I'm going to use calculus, right? And the idea here is that, remember, calculus is going to tell me that this thing is going to reach its maximum height, and then it's going to turn around and go back towards the ground. So what's the slope of that tangent line at that maximum height? It's 0. So I'm going to use that idea that the maximum height has to be when the velocity is equal to 0. So if I come down here to velocity, negative 32t plus 160, there's my velocity, which, by the way, just answered that question, the velocity at any given time. Okay. So now if I want to find out how high it goes, I just set that velocity equal to 0 and solve the equation. So we get negative 32t equals negative 160. T equals 160 over 32. Most of the numbers are supposed to come out nice in these problems. This one does, right? 32 times 10 is 320. So I guess that's 5, I hope. 5. So that's the time. That's not how high. That's the time when it reaches its highest point. So I want to know how high it goes. I got to plug that 5 back into my position function, right? Negative 16 times 5 squared plus 160. That would be the height. I'll whip out my calculator. These are meant to be done without calculator, but if you want to just do a calculator, do some quick math, that's fine. Just don't use the calculator to draw a parabola. That's not the idea here. So it's negative 16 times 25 plus 160 times 5, 400 feet. Okay. Next question was find the acceleration at any given time. The acceleration at any given time is just the derivative. Remember, acceleration is derivative of velocity. So acceleration is the derivative of this negative 32t plus 160, just negative 32, which is that gravitational constant, right? And then the last question is, when does it hit the ground and how fast it's going? When it hits the ground, that's not calculus. That's algebra, right? So if I wanted to know when something hits the ground, I got to take this position, which is negative 160, negative 16t squared plus 1, and set that equal to 0, because that's when it's going to be on the ground. If I factor out a negative 16t, you can use the quadratic formula. However you feel comfortable, you can factor. But if I factor out this negative 16t, I'm left with t minus 10. So I get t equals 0 and t equals 10. So at time 0, it's on the ground, which we knew, and then it hits the ground at times 10. If I want to know how fast it's going when it hits the ground, I plug that into velocity, right? So velocity is negative 32t plus 160. I plug in that 10. And I get negative 160 feet per second, which we also knew because think about the parabola. That was my initial velocity. It's got to be the same when it hits the ground, as long as it's starting on the ground. If it's not starting on the ground, that's going to change. So this is a little bit of a review of Algebra 2, but also the connections between calculus. Other than, if I ask you to find the velocity of the time, you have to use calculus. But theoretically, you could find heights and distances without calculus, but the velocity equals zero is a nice little calculus connection between the vertex of the parabola being there. So hopefully that's enough to help you out. Again, as always, please, please, please don't hesitate to ask me questions if you need some help. I'll see you tomorrow or the next day or whatever day it happens to be.